So, in this lecture we shall be looking at some of the techniques to reduce power at the level of gates, at the gate level. Okay. There are many interesting techniques which you can use by analyzing the signal activities that take place at the level of gates. So, we shall be looking at some of the quite commonly used approaches in this regard. Fine. So, we shall look at, as I said, various techniques for reducing power for designs which are expressed at the level of gates. Means here we may not be directly looking at the level of transistors. Well, in some approaches of course we shall be looking at, but in some of the approaches we shall be creating an abstraction, we shall be looking only at the gates without going into the transistor level details. So, even at the level of gates we can do some analysis and you can do some restructuring, thereby we can reduce the power consumption. Okay. Now, the advantage of these gate level design techniques for reducing power is that these methods can be quite easily integrated as part of the synthesis tools, like the CAD tools which are there, these can be integrated there itself. And of course, one very important design principle that is being followed is that you try and incorporate power aware design philosophy from the very beginning. Do not wait till your other things have been done, only at the end you start thinking about power. Do not do that. Even from the very high level, starting from the behavioral description itself, you keep at the back of your mind that your final circuit has to be power aware, has to consume less power, unnecessary power consumption should be stopped. Okay. These are the things that have to be kept in mind. This will simplify the problem later, of course. Yes. So, just recalling the power consumption in a CMOS network. So, I have this PMOS, CMOS, this is ground, this is VDD. Well, here I am just showing that earlier I had shown only the load capacitance, but in practice this capacitance will be sum of several things. This sigma C input is the load capacitance, which is due to the driving of the gate of the other transistors. There can be the parasitic capacitance of the interconnects, this long interconnection line, and also the drain capacitance of the local transistors. So, sum total of all of these, that will be the effective load capacitance that the output will be driving, right. And well, this is a simplified equation. I am assuming that in every cycle which is 0 to capital T, the output is being switched from, let us say, 0 to V out and then from V out to 0. That means, one is charging and discharging. So, I am showing the power consumption, average power consumption 1 by T in two parts. I am saying that for half the cycle 0 to T by 2. So, the voltage of this node is V out. So, this is discharging C load dV out dt, and in the other part you are charging. So, now the voltage difference is VDD minus V out, VDD minus V out. So, if you take this sum total, you will get the average power consumption over both the cycles, charging and discharging. Okay. And the other thing I want to also show with respect to this diagram is that, you see, you recall the average power dissipation expression. So, we showed an expression earlier which looked like alpha C VDD square into f, frequency of clock, but now we are refining this equation a little bit. We are saying is that, well, VDD into f clock is there of course, but here whenever we look at the charging and discharging of the capacitor, so it is not only the output node. See, all the other internal nodes of this gate, like here there is another junction out here. So, here also there will be an internal capacitance from this drain to ground. Okay. this is also not very negligible. Okay. This also has to be considered. So, whenever the inputs are changing, it is not only this load capacitance which is charging and discharging, but also this C internal which is charging and discharging. Like for this example, this is a 2 input NOR gate. Let us say V A and V B, the 2 inputs are changing like this. V A is going from 0 to high, V B is going from high to low. So, V internal, so whenever V A is conducting, so the V D D will come here. So, whenever V A is conducting, that means it is 0. So, V D D will be connecting here, it is 0, it is connecting here, the other time it will be 0, right. So, V internal will also be going through a charging and discharging phase. So, C internal will also go through charging discharging. So, here you have to consider this charging discharging for all the nodes, not only the output node, right. So, this is activity of the different nodes, activity of this node, activity of this node, the corresponding capacitance and the corresponding voltage. This is V out, this is V internal. So, this will be a more accurate calculation of the power, right. Okay. Now, let us look at the gate level design considerations. So, at the level of gates, we are mainly concentrating at the dynamic power consumption. So, we have seen that the main reason for dynamic power consumption and also the short circuit power is whenever the gate output is switching state 0 to 1, 1 to 0. So, some signal activity, we want to estimate the amount of signal activity that is possible in a circuit, right. So, there is an objective function, we shall be explaining this a little later. This objective function we shall basically come back to it, where C denote the capacitance of a node, Pi denote the probability. Okay, this P does not denote the power, but it is the probability that the logic value of a node is at logic 1. You see, let me talk about the justification, Pi into 1 minus Pi. You see, Pi is the probability that a node is at 1 and 1 minus Pi is the probability that the node is at 0. Now, at a node, when there will be power consumption, when there will be a transition, right. Actually, when there is a transition, that the value of the node is sometimes high and sometimes low, then only there will be a transition. So, what will be the probability of that? Probability of high is Pi and probability of low is 1 minus Pi. So, I take the product of these two, Pi into 1 minus Pi. If I take the product, it means I am saying that this is the probability that the logic value of the node will be at 1 and also will be at 0, which means there is a transition, or vice versa 0 and 1, right. That is why I take the product of Pi and 1 minus Pi, that is the probability that there is a transition, multiplied by the capacitance value. So, if you take the sum total, this will be the objective function that I want to minimize, because if I minimize this, my dynamic power will also be minimum. Okay. Fine. So, there are many approaches which are used, we shall be looking at some of these approaches one by one. Technology mapping, phase assignment, pin swapping, glitching power, etc. We shall be seeing these methods. So, let us start with the technology mapping approach. See, what is technology mapping? During logic synthesis, so what is logic synthesis? Given a specification, I want to generate either a gate level or a cell level circuit. Technology mapping means I have a library where some standard cells are already present, maybe 2 input gates, multiplexers, this kind of things. So, when I synthesize, my basic building blocks must be taken from that library only. This is called technology mapping. I generate a netlist of cells where the cells are picked up from the technology library. This process is called technology mapping. Okay. Fine. So, here assuming that my technology library consists of 2 input gates, which is quite true. Of course, a few other type of gates are also there. So, here we are trying to define an objective function where we are minimizing or trying to minimize the total switching activity, because we know that the power consumption is greatly dependent on the switching activity. Okay. So, we illustrate the process with the help of an example. So, we take a 4 input circuit with inputs A, B, C and D. See, the idea is as follows. Let us say I have a circuit, there are 4 inputs A, B, C, D. Now, in this approach, of course, there is an output. In this approach, we are looking at the signal probabilities. So, I am assuming that the signal probability of the inputs A and B are 0.2 and 0.2 and C and D are 0.5 and 0.5. Well, you can ask that how do I know these values? Well, you see, there can be some circuit from the output of which you are driving A, there can be some other circuit from where you are driving B. These circuits can determine that how frequently the output can be 1, output can be 0. There is a simple probability based calculation, we shall be looking at it with respect to a block, that how this probability calculations are done. So, 0.2 means the signal value at line A will be 1 with 20% probability, will be 0 with 80% probability, right. Similarly, C and D will be equal 50%, 50%, all right. So, the estimation of the activity factor, this is important. So, here we are saying Pi will denote the signal probability at node I, as we have just explained some time back. So, we use this notation Pi to denote the signal probability of node I, which means what is the probability that the particular line will be at logic 1. So, the probability that the node is at logic 0 will be 1 minus Pi, okay, because the total probability has to be 1. So, activity factor from the consideration I explained just now some time back, alpha I we defined as the product of Pi and 1 minus Pi, because there will be an activity whenever the node will be at 1 and also will be at 0, then only there will be a transition, right. So, when the data which is coming is totally random, which means they are equally 0 or 1, the probabilities are equal. So, there is a 0.5 probability it is 1 and 0.5 probability it is 0, when the data is totally random. So, for totally random data Pi will be 0.5 and hence alpha I will be 0.25. But in real circuits data will not be totally random. So, the activity factors will typically will be much less. So, we shall be working out a simple example, but before working out the example, we look at how to compute the signal probability of the basic gates. See, this equation may look a little complex, but the way they have been obtained are pretty simple. Consider a 2 input AND gate. This is the probability that the input will be at 1. So, what will be the probability Pf? The probability output will be at 1. For an AND gate, output will be 1 if both the inputs are 1. So, it will be the product of Pa and Pb, right. Similarly, if you look at an OR gate, same way, 2 inputs, the signal probabilities are Pa and Pb. So, what will be Pf here? See, for an OR gate, okay, when will be the output be 1? Well, the rule is at least one of the inputs are 1, but it is difficult to write down probability that way. It is easier to write the probability that when the output will be 0, let us see that way indirectly, the output will be 0 if both the inputs are 0, right. So, what is both the input are 0 means 1 minus P A, 1 minus P B. So, 1 minus P A multiplied by 1 minus P B, this is the probability that f will be 0, right. But we want the probability f is 1. If this is the probability of f is 0, then 1 minus of this will be the probability f will be 1. This whole thing will be probability f is 1. So, it follows like this, right. So, if you now look at the table, you can justify the other ones. For a NAND gate, it will be just the reverse of AND gate. The output of AND gate will be 1 if both are 1 1, but NAND gate will be 0. So, it will be 1 minus of this. NOR gate, this 1 minus will not be there. See XOR gate, PA is 1, but PB is 0, or PA is 0 and PB is 1. For a 4 input AND gate, all the 4 are 1s. 4 input OR gate, just an extension of this, all 4 are 0, 1 minus of that, right. Okay. So, we shall be working out an example like this. I shall be showing you step by step evaluation. So, what we are basically saying is that I have a function which is a 4 input AND, but my technology library has only 2 input AND. So, I can either partition my design like this, or I can partition it like this. So, I do not know which one of them is better. Well, obviously, from the point of view of delay, this one will be better because there are 2 levels of gate delay, but here there are 3 levels of gate delay, delay will be more. But from power consumption point of view, which one is better? Let us see. So, I have assumed that the signal probabilities are like this 0.2, 0.2, 0.5, 0.5. Let us work out. First, let us look at this alternative, the first way of mapping, where delay is 3 units. So, we are estimating power. So, what we have assumed? We have assumed that the input signal probabilities are this 0.2, 0.2, 0.5 and 0.5. So, we first calculate the probability values of the other lines just using those tables. So, what will be PE? It will be product of PA and PB. So, let us see, PE will be this is an 2 input AND gate, product of PA and PB, just multiply 0.04. PF will be product of PE and PC, 0.04 into 0.5, it is 0.02. And what is PG? PF multiplied by PD, 0.02 multiplied by 0.5, 0.01. So, we have calculated the signal probabilities. Now, let us calculate the alpha I values, the signal activity values. Now, alpha by definition is defined as P multiplied by 1 minus P. So, on this line E, alpha will be P into 1 minus P, P is already calculated. So, if you just substitute, it will be this. Alpha F similarly will be this, and alpha G will be this. So, for this circuit, the sum of the signal activities, if you just add them up, so total switching activity will be 0.0679, right, for this kind of an alternative. But now, suppose we map the gate in this way, where the gates are in 2 level, obviously delay is less, the gate will be faster, but with respect to power, let us see the same probability values. Now, P values will be like this, P will be similarly PAPB 0.4, PF will be PC into PD 0.25, PG will be P into PF 0.01. So, if you calculate now alpha E, alpha F and alpha G, you will see the values are coming like this, where the value of alpha F is significantly higher, right, and the total signal activity is also much larger. In the earlier case it was about 0.06 something, right, here it is 0.23. So, from the point of view of power dissipation, this is a very bad technology mapping. So, what we are saying is that normally during technology mapping so far we did not look at power, we simply looked at the delay, how fast the circuit can work. But now there is an additional parameter. During technology mapping you can have another objective function which will calculate the sum total of the signal activities, the activity factors alpha I, and tell you among multiple alternatives which one is better with respect to power. Also you know which one is better with respect to delay. Then it is a trade off that you will have to decide that what is your objective. Okay, fine. Okay. There is another technique which talks about something called phase assignment. Here you can move a gate across functional blocks to reduce the activity. I am giving a very simple example. Here we have a gate level circuit, just two gates which computes the function a bar b. You see that there is an inverter on input A. Let us assume that this line A is a high activity node where there is lot of signal activities. The value of PA is higher. Okay. So, because PA is higher, the output of this inverter will also have a higher value of P, because for every transition in the input there will be a transition in the output, right. But suppose I make a technology mapping of this circuit like this, so that I modify this AND gate into a NOR gate and I change my input B from B to B bar, such that my output function remains the same, right. But what I have achieved is that earlier there are two nodes that were high activity, but now there is a single node which is high activity, right. So, naturally my power consumption will be reduced. So, we try to move gates around in sections of the circuit where some higher activities are envisaged, and you try to reduce the sum total of these activity factors, again alpha I values, by moving the gates around, restructuring gates, using Boolean algebra rules to change the functional behavior. Like here we have modified an AND gate into a NOR gate, just like that, right. Fine. Let us take another example, say a multiplexer. Suppose I have a 2 to 1 multiplexer where there are two inputs A and B, A is inverted, and incidentally let us suppose A is a high activity node. So, the output of this NOT gate will also be high activity. So, what I do, I modify the circuit. So, I take out the inverter from here, I put the inverter on line B, and also I put an inverter on the output. So, functionally my multiplexer remains the same because there will be two inversions, but what I have achieved, instead of two high activity nodes, now I have a single high activity node, because output whatever it was, it remains same, there is no change, right. So, these are some simple examples which show that you can make some changes in a circuit netlist and also some functional blocks you can modify, so as to reduce the signal activities, right. Okay. Let us look at some more techniques. There is a technique called pin swapping. You see, this is an interesting thing. So far we have not considered this at all. Like what I am saying is something like this. Take a multi input gate. Suppose I have a 4 input NAND gate, let us say. Normally when we have a multi input gate, so we connect ABCD like this. Suppose we have another scenario, same gate, but we connect the gates like say ADCB. Now, because the NAND function is commutative, Well, you can easily say that these two are equivalent. These two are equivalent functionally, of course, but you may also be tempted to think that, well, functionally they are equivalent, power dissipation wise also they should be equivalent, because if there is a signal activity in one of these, there will also be a signal activity in the other one, and vice versa. But in fact, in CMOS this does not always happen. This is interesting. So, here what we say is that the impact of the switching activity of a gate input with respect to power dissipation depends on the relative position of the input. So, now we have another design flexibility or parameter. We can put the higher activity nodes to the inputs whose impact on power dissipation is the least. So, we are explaining this with the help of an example here. We take a 4 input NAND function. Say the inputs we have connected are as follows: D, C, B, A, and this slide shows red means maximum activity, this lighter shade means less activity, which means the alpha value for D is the highest, alpha value for A is the lowest. Now, the observation here is follows. You see, here we have only shown the load capacitance here, but as I said, there will be a capacitance with each of these intermediate nodes. So, if this node D switches very fast, this is red, okay, then due to some leakage current here or whenever this was on, this capacitance charging discharging will also be quite high, alright, because there will be a conducting path through here for some time. Similarly, C is also quite frequently switching. So, there will be times when both D and C will be conducting, and this capacitance will also be charging and discharging. Okay. But if we put it the other way around, the least active input we put at the top. So, this transistor will be mostly non-conducting. So, even if the lowest transistor is very heavily switching, so the current switching and charging discharging impact will be the least, because it is just down the stack, lowest down the stack, right. So, this is one design philosophy you can adopt, where looking at the signal activity of the input, you can push the highest activity node to the lowest input, like here A, B, C, D will be a better input assignment rather than D, C, B, A. Okay. So, with this we come to the end of this lecture. Now, in the next lecture we shall be looking at some more techniques at the level of gates by which you can control or reduce the power consumption in the circuit. Thank you.